Welcome students. We want to discuss about the dot product of two vectors. So until now we have learned how to multiply a scalar with a vector. So if we had a scalar C, so if we take C to be an element of R and let V be a vector, so V belong to, say if I want to talk about 2 by 2 vectors, my V is a 2 by 2 vector where V can be written as v1, v2, then we have learned how to basically multiply a vector with a scalar. That would be essentially cv1, cv2. Now we want to multiply two vectors in a meaningful way. Again, what does it mean by meaningful way? We want to have some physical interpretation of it, or it has some sensible, or we need some sensible way of combining two vectors. So one of the motivation comes from the following: find angle between vectors A and vector B. Yeah. So we will come with one of the product of two vectors, which is called dot product, or also called as scalar product. So what is the dot product or scalar product? So, so dot product of two vectors, A, which is given by A1, A2, A3, and B, which is given by B1, B2, B3, is defined to be A dot B is A1 multiplied by B1, A2 multiplied by B2 plus A3 multiplied by B3. So this is the dot product, all right? So it's also called scalar product because the output of this product is scalar, right? So you see that A1, A2, A3, B1, B2, B3 belong to R. So in this case, we have A1, B1 plus A2, B2 plus A3, B3 belongs to R as well, right? So this belongs to R. And hence, this is a scalar product. So let's compute dot product of these two vectors. So A dot B is going to be A dot B is going to be A1 B1. So 5 times minus 3 plus 7 times 4 plus 0 times 2. And the output is, so 5 minus 15 plus 28. That is going to be 13. So this is the dot product of this. Now there are few properties of dot product, namely A dot A is length of A the whole square. That is not hard to see. Why is that? Because A dot A is going to be A1, A2, A3 dot B1, A1, A2, A3 which is A1 square plus A2 square plus A3 square, which we know is going to be, this is basically length of A the whole square. Yeah. So similarly, the other formulas can be verified, namely A dot B is same as B dot A. A dot B plus C is A dot B plus B dot plus A dot C. This is distributivity of dot product over addition. C times A dot B is C times A dot B, which is A times A dot CB, and 0 times A is 0 as a scalar. So these are the few properties of dot product which can be verified very quickly. Now we want to talk about the geometric interpretation of dot product. All right, without geometric interpretation, defining an object would basically make very little sense. So let's find out what does the dot product signifies. So let's take a vector A, let's take a vector B. So this is vector A, this is vector B. and let theta be the angle between them. So then this vector joining here can be written as this vector can be written as what? So this can be written as A minus B, and that theta be the angle between them. So let's use the law of cosine on this thing. So just to label things, so we call this as O, let's call this as point A, let's call this as point B. Okay. So what do we get in this case? So we have, using law of cosines, we'll have AB square equals to OA square, length of OA square, plus length of OB square, minus 2 length of OA, length of OB, times cos theta, where theta is the angle between these two guys. So now AB, length of AB is vector A minus vector B. This is going to be length of vector A square plus length of vector B square minus 2 length of vector A times length of vector B times cos theta, where theta is the angle between them. Now, what is A, vector A minus vector B, the length of it, the whole square? We already have that. It is going to be A, so length of A square is A dot A. So this is going to be, so let's work it out. The left-hand side is A minus B dot with A minus B. Now we use the property of distribution here. So this is going to be A dot A. So first I'll take this guy and multiply with this and this. So we get minus A dot B. Then we have minus B dot A. So now we are going to multiply this one with here. We get B dot A, and then we multiply this one with this. We get plus B dot B. So this is going to be length of A square minus 2 A dot B, because A dot B is same as B dot A, plus length of B square. Now, what is your RHS? RHS is OA, which is length of A square. OB is length of B square minus 2 OAAB, which is length of A minus length of B times cos theta. So if you equate these two, you will see that you can cancel out, we can cancel out this guy with this guy, we can cancel out this guy with this guy, sorry, this guy with this guy. So what do we get out of this? We get, this implies minus 2A dot B equals to minus 2 length of A, length of B cos theta. Cancelling minus 2 from both sides gives us A dot B equals to length of A, length of B cos theta, where theta is the angle between these two vectors. Now note that this is true, this kind of definition is only for non-zero vectors. So here we go. So if A is a angle, if theta is the angle between two non-zero vectors A and B, then cos theta is given by length of A. So A dot B divided by length of A times length of B. I don't need to put an arrow because by boldface we already mean that they are vectors. So we have given a physical interpretation or geometric interpretation to the dot product. Very cool. So now let's use this to find out angle between vector A and vector B, which are given here. So angle between them is given by, so if theta is the angle, then we get cos theta, or between them, between A and B, then we get cos theta equals to A dot B divided by length of A, length of B. So what is A dot B? 3 times 0, which is 0, 0 times 4, which is 0, plus 4 times 3. So 3 times 0 plus 0 times 4 plus 4 times 3 divided by length of A, which is going to be what? Square root of 3 square plus 4 square. B, length of B, which is 0 square, so 4 square plus 3 square. This is going to be 12 divided by, this is 3 square plus 4 square is 16 plus 9, which is 25. So square root of 25 divided by square root of 25, which is 12 by 25. Therefore, theta equals to cos inverse of 12 by 25. Okay. Now, two non-zero vectors. So if the angle between two vectors is 90°, then we call them perpendicular, right? So the proper way to put that is two non-zero vectors A and B are perpendicular if and only if A dot B equals to 0, right? So clearly you have A dot B equals to length of A, length of B, cos theta. Now, if these vectors are non-zero, and if we get this equals to 0, that would imply cos theta equals to 0. This implies theta equals to pi over 2, because we are looking in the range from 0 to pi. Okay. Now, let's look at the following. So check if vectors A and vector B are perpendicular vectors. So what we'll do is we'll take the dot product. So A dot B is going to be 3 times 2. So 3 times 2. So 3 times 2 plus 4 times minus 4. So 4 times minus 4 plus 5 times 2, which is going to be 5 times 2. So what is that going to be? 6 minus 16 plus 10, which is 0. So therefore, A and B are indeed perpendicular. Now, sometimes it is important to know, if you take a vector A, what angle it makes with the positive direction of x-axis. Let's give that a name alpha. What angle does it make with the positive direction of y-axis? So this is your x, y, and z. What angle it makes with the positive direction of y-axis? Let's call this beta. And then let's the angle it makes with the positive direction of z-axis. So let's call that as gamma. Okay, so this is alpha, beta, and gamma. So these angles are called direction angles. So direction angle of a non-zero vector A are angles alpha, beta, and gamma that it makes with positive direction of x-axis, y-axis, and z-axis. Now, we need to find out, if I give you a vector A, is there a way to find it out? So how would we go about it? So let's take, so we know the vector, which is, if I give you vector A, how can you find out alpha? So note that the unit vector along the x-axis is I, along the y-axis is j, along the z-axis is k. So let's find out uh, what will be the alpha. So the alpha angle. So we have cos alpha using the dot product is going to be a dot I divided by length of a times length of I. So that is going to be essentially, if you have vector a as a1, a2, a3, then this is going to be a1, a2, a3. And what is vector I? Vector I is given by 0, 1, 0, 0 divided by length of this, which is going to be length of a1, a2, a3 times length of vector 1, 0, 0. We know that that's a unit vector. So we get, in this case, we get a1 divided by length of vector a. Similarly, cos of beta is going to be a2 divided by length of vector a, and cos of gamma is going to be a3 divided by length of vector a. So this is how we get the direction. If you take cos inverse of this, you'll get direction angles. Now, notice the following. So from here, we can get, so let alpha, beta, and gamma be the direction angles. Find the components of vector A. So clearly from here, you can see that the components of vector A are given by A1. A is given by A1, A2, A3. And if we look from here, A1 is going to be, if we use this one here, we get A1 equals to length of A cos alpha, length of A, that A2 is going to be length of A cos beta, and A3 is going to be length of A cos gamma. Another relation, interesting relation we can find between these guys is the following. So we have, if we look at cos square alpha plus cos square beta plus cos square gamma, this will be 1. Okay, so this is the relation between the cosines of directions, angles. Now to see the proof of this, it's not hard. Why? Because length of A from here is going to be, or length of A square is going to be length of A cos alpha, the whole square, plus length of A sine cos beta, the whole square, plus length of A cos of gamma, the whole square. And if you cancel out the common factor of, so dividing throughout by length of A the whole square will give us 1 equals to cos square alpha plus cos square beta plus cos square gamma. Okay, so this is a connection between alpha, beta, and gamma. Now this connection can be really useful if you know alpha and beta, the direction angles, and you want to find out gamma. And similarly, if you're given the other two, you can find the other missing ones. So let's look at the following. Find the direction angles of vector B, which is this. So, well, in this case, your B, so you get cos beta, sorry, let's start with cos alpha, is B1 upon length of B. So let's compute length of B. So length of B is going to be square root of 2 square plus 4 square plus 2 square. So this is going to be 4 plus 4, 8, 8 plus 16. 16 plus 8 is 24. So square root of 24, which is, you can take 4 out. So square root of 6 times 2. So cos alpha is going to be b1. So 2 upon 2 times square root of 6, which is going to be 1 by square root of 6. So therefore, alpha equals to cos inverse of 1 by square root of 6. Similarly, cos beta is going to be b2 upon length of b, which is going to be minus 4 upon 2 times square root of 6. This implies beta equals to cos inverse of minus 2 by square root of 6. Similarly, cos gamma is going to be b3 upon length of b, which is 2 over 2 square root of 6. This implies gamma equals to cos inverse of 1 by square root of 6. So this is how you find the direction angles for given vector b. Now, another interesting aspect is, and we'll see the physical interpretation of it when we are looking at the work done, is the following. So you are given a vector A. So this is your vector A, and when we have vector B. So this is vector B. And what we are interested in is, what is the projection of vector B onto vector A? Now, one way to think about this is, we are interested in, when we project down this vector, what is the corresponding length of this vector here? So this part here is called component of B along vector A. So let's find out, how do we go about it? So we have the following. So we want to find out what is the projection here. So this part is going to be, if this angle is theta, this part is going to be B cos theta. Yeah. Where B, by B we mean, so well, okay, let's take this as a vector, then we are interested in the length of vector B. So this will be this length of this green line segment is the projection. It's a scalar projection. So let's compute the scalar projection. So the scalar projection, so we have scalar projection is given by B cos theta. So this is given by the scalar projection. Let me write that again. One way to call this is component of B along A component of scalar component of B along A is given by B cos theta, which is going to be divide and multiply top and bottom by A and B, sorry, length of vector A on top and bottom we have, and that can be seen as A dot B over length of vector A. So this is how we find out the scalar projection. Now, what is a vector projection? So vector projection is, again, same story. We have We have vector A, we have vector B, and we want to talk about the vector projection. So the vector projection is this vector here, starting from here to here. So this is a vector, it's called projection of B onto A. So projection of B onto A. Now note that what kind of vector is this? This vector has same length as the component, right? It's the same length as the component, which found out to be A, B divided by length of A. But this is a scalar quantity. We need to give it a direction. What direction? We need to give it a direction of vector A. So let's multiply by direction of vector A. So we'll multiply by unit vector. So it's going to be, so this is a projection of B onto A. This is a vector projection. And if you want to simplify it a bit, it will look like A dot B divided by length of A whole square. Now note that this is still a number and you are multiplying, you're taking, this is a scalar, so you're multiplying a scalar by to a vector. Okay, so this gives you the vector projection. So two kind of projection, scalar projection and vector projection. Yeah, scalar projection, which is a component of B along A, is a number, whereas the vector projection, which is given by projection of B onto A, is a vector projection. Okay, so now let's do a computation. So find scalar projection and vector projection of B onto vector A. So how would we go about it? So let's write down first. So component of B along A, we have already derived a formula for it. So let's use that formula. So it's going to be A dot B over length of vector A, which is going to be A dot B. So this is 2, 1, 1 times dot width 3 minus 2, 4 divided by length of A, which is 2, 1, 1. And that is going to be, so let's look at the dot product. So 2 times 3 is 6. 6 minus 2 plus 4 divided by square root of 2 square plus 1 square plus 1 square. So 4 plus 5, so 6. So we get 6 minus 2 plus 4, which is 8 over square root of 6. So this is the scalar projection. Now what about the vector projection? So now vector projection of B onto A, either I can use this formula here, or I can just take the component, reuse what we have already computed and multiply it and give it a direction of vector A divided by length of A. So this is going to be 8 over square root of 6. Vector A is going to be 2, 1, 1 divided by length of vector A again, which is going to be square root of 6, because that computation we have already done here. So if we rewrite it properly, this is going to be 8 by 6, which is going to be 4 over 3 times multiplied by 2, 1, 1. So this is the vector projection of vector B onto a vector A. Now, this has a quite an interesting significance, uh, the concept of work done. So recall, until now, if you have seen in physics, the work done by a constant force F in moving an object through a distance d is given by F dot d. Yeah, so if you have a force, you basically have moved, and your force is acting in this direction, your object moved from here to here, d, then the work was basically F times d. Yeah, and there was This was done in the same line along this guy. So you just multiplied force and the distance. However, we want to understand a slightly different scenario, namely where you have the force is, so suppose you have a force now, so we want to have a vector version of this. Why? Because the force and the displacement are not in the same direction. So suppose you have the following. You have force which is given by PR is acting on a particle here, and the displacement happens from P to Q. So let this angle be theta, and we want to basically find out the work done. So this PR is your force as a vector acting on the object, and the displacement D is equal to PQ. Now we want to basically find out what is the work done. So this is your displacement, and this is the force. So now if this is a distance traveled, so D is going to be length of PQ. Now what is the work, what is the force acting in the direction of displacement? So that is essentially, this is the amount of force acting in the direction of the object. Now that is given by F, length of F times cos theta, right? Because we are looking at the length of this object, which is your component of vector B along A. In this case, it's the component of force vector along the displacement. This is given by, so force, so work done, which is a scalar object, is the component of force along PQ times the displacement, which is length of PQ. Or if you want to give it a name, this D, it will be basically F cos theta times PQ, and PQ can be written as D, so it is essentially length of vector D. And if we interpret this as dot product, this is going to be F dot D. So this is one interpretation of work done using dot product. Okay. So let's look at an example. So we have the following: a wagon is pulled a wagon is pulled a distance of 10 meters along a horizontal path by a constant force of 70 Newton. Okay, so the force acting on the object is 70 Newton, and the handle of the wagon is held at the angle of 35 degrees, all right, above the horizontal. Find the work done by the force. So you have a wagon, and we have, this is the horizontal, and your force is what? The handle of the wagon is held at the 35 degrees above the horizontal. So you have basically, the force will be applied in this direction, right? Because you have this handle and you are pulling it with the handle. So this is where the force is acting, and it's creating the displacement in this direction. So work done would be F dot D. Now instead of finding F as a vector, we can use the length of F times length of D times cos theta. And that would give us, well, length of F is 70. D is how much distance has been pulled? 100 times cos theta, which is going to be cos 35 degrees. Yeah. And if you want to approximate, so this is the answer. If you want to really multiply it out, you will see that that's going to be 75734 Newton meter. Yeah, and Newton meter is also referred as joule. So yeah, joules. Okay, but this is the part here, right? Yeah. So this is how we basically understand uh, the work done by the force. Now let's look at another example. Example 8, example 18. So, suppose a force F, which is given by 3I plus 4J plus 5K, moves the particle from point P, say which has coordinate 2, 1, 1, to Q, which is 3, 4, 2. Find the work done. Okay, so how would we go about it? Again, F is already given to us. We need the displacement vector D, which is vector PQ, which is OQ minus OP, the position vector of Q minus position vector of P, which is 3, 4, 2 minus 2, 1, 1. That is going to be 1, 2, 1. So therefore, work done is F dot D, which is going to be F, which is 3, 4, 5. That's another way of writing the same thing, times 1, 2, 1, which is 3 plus 8 plus 5, which is going to be 13 plus 3, which is 16 units. Yeah, of gain. I mean, that this units could be specified if basically if force was measured in, if length was in meters and the magnitude of force is Newton, then the work done would be in joules. Okay, so that's about it. Thank you for your attention.